Imagine you're plugging a tiny, like, 2 GB flash drive into this massive $40,000 server-grade GPU.
Oh, yeah. The dream setup.
Right. And you've got this incredible open source AI model on that drive, say, I don't know, a 7 billion parameter model.
Sure.
You fire up the system, you tell the model to learn something new, and instantly, just instantly, the entire supercomputer crashes.
Yep. The classic red text of death.
Exactly. The screen just spits out that dreaded red text out of memory. And you're just sitting there, right, thinking, how did this hardware, which is practically a supercomputer, just choke on a file that I can literally fit in my pocket?
It's honestly the ultimate collision between theoretical software and just harsh, unyielding physics.
Yeah.
You can write the most elegant code in the world, I mean, truly beautiful math, but if the physical silicon on your graphics card doesn't have the literal microscopic space to hold the electricity representing that math.
The universe breaks.
Exactly. The universe breaks. It just stops.
Yeah. So today, for this deep dive, we are tearing open that physical silicon to find out why that happens. We're taking like a really intricate microscopic journey into the hidden physical reality of deep learning.
And it is a wild journey.
It really is. We're going under the hood of the GPU, specifically looking at the high bandwidth memory, or HBM, to examine the literal building blocks of AI. We want to make this deep dive as long and as detailed as possible so you, the listener, really get a grasp on this.
Because it's so important.
Right. We're going to look at everything from the single 4-byte parameter to the completely invisible 8-byte optimizer states, which, kind of act as the model's memory.
Oh, the optimizer states.
Yeah.
The silent killers.
Seriously. And then we'll get into the explosive, dynamic size of activations. Plus, we're going to uncover the clever, almost magical illusions that PyTorch uses to, manipulate billions of numbers without actually moving a single one of them.
I love that part, because we so often treat artificial intelligence as pure abstraction.
Yeah, like it's just floating in the cloud.
Right. We talk about neural networks as if they are biological brains, or just these beautiful equations floating in a void. But the source material we are diving into today strips all of that away entirely. It reveals that training an AI is a grueling, industrial-scale exercise in physical logistics.
Physical logistics, that's a great way to put it.
Yeah, because every single calculation, every single parameter demands physical real estate on a microchip. And understanding that physical cost isn't just like trivia for hardware nerds.
No, not at all.
It is the absolute prerequisite to mastering AI.
Right.
If you can visualize the memory, you can control the model.
So we really have to start at the absolute foundation. If we want to understand why this massive GPU ran out of memory, we need to look at the smallest unit that's actually taking up that space.
The atomic unit.
Right. In a neural network, that atomic unit is a parameter, a weight. It's just a number, but it's not just a conceptual number, right?
I know, it has a very specific physical shape.
Exactly. A shape dictated by this decades-old computing standard, the IE754 single precision floating point format, or as anyone in machine learning actually calls it, FP32.
Yeah. No one is saying the full IE name in the lab. It's just FP32.
Yeah.
And it's the bedrock of modern computational math.
Right.
When you read a headline that says a new AI model has 7 billion parameters,
Yeah.
you really need to train your brain to translate that instantly.
To what?
To realizing it means the model consists of 7 billion individual FP32 numbers sitting in a vast grid in the silicon.
So let's actually visualize one of those numbers for you listening right now. What is physically inside an FP32?
Well, the 32 is a huge clue.
Right. It stands for 32 bits. And a bit is just a single transistor holding an electrical charge, right? A 1 or a 0.
Exactly. The fundamental coin flip of computing.
And since there are 8 bits in a standard byte of data, 32 bits means every single parameter takes up exactly 4 bytes of physical memory space.
4 bytes. It sounds so small.
It does. But it isn't just 32 random coin flips. It's this incredibly rigid, brilliant architecture designed to represent both massive numbers and microscopic fractions simultaneously.
It really is a marvel of engineering. The architecture is broken into 3 distinct segments.
Okay, break them down for me.
So the very first bit is the sign bit. It has one job. 0 means the number is positive, 1 means the number is negative.
Okay, 1 bit down, 31 to go.
Right. The next 8 bits form the exponent. The easiest way to conceptualize this is to think back to high school chemistry.
Oh, boy. Scientific notation.
Exactly.
Yeah.
Scientific notation. When you write a number like 6.02 times 10 to the 23rd powers.
Avogadro's number, I remember that much.
You got it. The 10 to the 23rd part dictates the massive scale of the number. It tells the decimal point where to move.
Okay, yeah.
The 8 bits of the exponent in FP32 do the exact same thing in binary. They determine whether we are talking about a number the size of a galaxy or a number the size of an atom.
So it's the scale, the power of whatever.
It's the scale.
And then the final chunk is the remaining 23 bits. That's called the fraction, or the mantissa.
Right.
So if the exponent is the scale, the mantissa is the detail. It determines how many significant digits we actually care about. It's the precision.
Exactly.
So packed into those 4 bytes, you have the sign, the scale, and the precision.
Which brings up a critical engineering debate in the field right now.
Huh.
Yeah, because computer science offers us a whole menu of these formats. So the question is, why did the entire AI industry settle on FP32? Why 4 bytes?
Right.
If we are trying to build the smartest artificial brains possible, wouldn't we want, more precision?
Yeah.
Why not use FP64, the double precision format that takes up 8 bytes?
Well, I would assume the physics of compute just make that a total nightmare.
It does.
Like if you double the size of every number from 4 bytes to 8 bytes,
Yep.
you instantly cut your GPU's memory capacity in half. And you have the speed data can travel across the memory bus. And for what? Like, a neural network isn't calculating the orbital mechanics of a satellite where the 15th decimal place dictates if you crash into Mars.
That's the perfect way to look at it. It just needs to know the general gradient, the slope of the air to tweak the weights. 8 bytes seems like massive overkill.
Is it overkill?
Oh, it is absolute overkill. Using FP64 for a neural network is like using an electron microscope to read a billboard on the highway.
Wow.
You are burning massive amounts of electrical power and memory bandwidth for precision that the neural network's inherently noisy learning process will just wash away anyway.
Because the data is noisy to begin with.
Exactly. FP64 slows everything down by a factor of 2 or more, with literally 0 improvement in the final intelligence of the model.
Okay, then let's go in the completely opposite direction.
Yeah.
If the model is robust to noise and doesn't need missile-level precision, why not just use 2 bytes? FP16, half precision.
A very tempting proposition.
Right, because if we switch to FP16, we instantly double the size of the model we can fit on our GPU, and we double the speed at which we can move those numbers around. Sounds like a win-win.
And we do use FP16, and increasingly formats like BF16, all the time, but primarily for running the model after it has been trained.
Oh, so just for inference.
Yes. When you are just generating text, FP16 is fantastic. But for the actual training process, for holding the master weights that are actively learning, FP16 is an absolute minefield.
Why? What goes wrong?
You run headfirst into 2 mathematical walls: gradient truncation and overflow.
Okay, let's break those down. How does gradient truncation actually happen mechanically? Like, why does the math break?
Let's trace a parameter that is trying to learn. During backpropagation, the network calculates a gradient.
Which is essentially a tiny suggestion of how much to change the weight to reduce the error.
Exactly.
A nudge.
Let's say that gradient is a very small number, like 10 to the -4th.
Pretty.
Right. Now, the optimizer takes that gradient and multiplies it by a learning rate, which is also very small, maybe another 10 to the -4th.
Okay, doing the mental math.
When you multiply those together, the suggested update to the weight is microscopic, 10 to the -8th.
Ah. And here is where the bits actually matter. If I'm using FP16, I only have 10 bits dedicated to the mantissa, the precision part.
Right.
And 10 bits simply cannot represent a number as small as 10 to the -8th, can it?
It cannot. The physical container simply does not have enough resolution. So the hardware looks at this microscopic update, throws its hands up, and rounds it to exactly 0.
Wow. Wait, really?
Literally 0.
So the neural network is doing all this massive calculus, trying to take a tiny, nuanced step toward intelligence, and the physical math format just says, nope, you're too small, I'm recording a 0.
And the model literally stops learning. It just freezes.
That's terrifying.
That is gradient truncation. But the other side of the nightmare is overflow.
Okay, what's overflow?
Well, FP16 has a maximum possible value of exactly 65,504.
That doesn't seem very high.
It's not. And in the chaotic, volatile early stages of training a massive network, the intermediate math inside a layer can easily spike above 65,000.
Just a random mathematical spike.
Right. And the moment a calculation hits 65,505, FP16 cannot represent it. The GPU literally outputs NaN, not a number.
Oh, I've seen NaN errors. And NaN is a virus.
It really is.
Because if one number in your billion parameter matrix becomes nan, the next matrix multiplication propagates that nan to everything it touches.
Exactly. Within seconds, your entire network is mathematically destroyed. It's unrecoverable.
So FP32 really is the Goldilocks zone. It has enough precision to not round microscopic gradients to zero and a large enough exponent to never overflow into nan.
That's it. This establishes our foundational law of physics for AI hardware. One parameter equals 4 bytes of VRAM.
Always.
Always. Which allows us to calculate what I call the golden rule of memory estimation.
Great. Let's do the math for the listener so they have this tool. Say you want to work with a 7 billion parameter model.
Okay.
You take 7 billion, multiply it by 4 bytes, and you get 28 billion bytes. That translates to roughly 28 gigabytes of video RAM just to store the basic static FP32 weights of the model.
28 gigabytes of pure silicon real estate just to load the file.
But wait, let's play this out. I do that math right. 28 gigabytes. I look at my computer case, and I have a top-of-the-line consumer GPU with 32 gigabytes of VRAM.
A beast of a card.
Yeah. I have 4 gigabytes of breathing room, so I can train this model right. I'm good to go.
Well, the math for the model is correct, but the conclusion is violently wrong.
Violently wrong.
You cannot even begin to train that model on a 32 gigabyte GPU. In fact, if you try to initiate a training loop, you will instantly run out of memory the moment you hit run.
How? Where's the hidden cost? The file is 28 gigabytes.
Because the file you downloaded is just the final frozen state of the brain. It is the static architecture. But training is not static. To actually learn, the optimizer software has to build a massive, invisible scaffolding around every single one of those 7 billion weights.
Ah, the scaffolding.
The weights are just the raw material. The optimizer is the heavy machinery. And that heavy machinery brings us to the biggest hidden tax in all of deep learning.
And this introduces, the sources refer to as the 8-byte mystery, the optimizer state.
Yes.
We are looking specifically at the industry standard optimizer called AtomW. We just established that the model's weight, its actual brain, takes up 4 bytes. But the AtomW optimizer demands an additional 8 bytes of memory for every single parameter, simply to track the history of how that parameter is learning.
And we really need to let the sheer scale of that sink in.
No.
For every 4 bytes of actual neural network, you must allocate 8 bytes of historical bookkeeping.
It's a 2-to-1 ratio of overhead to actual product.
It's insane. A 7 billion parameter model doesn't just need 28 gigabytes. It needs an additional 56 gigabytes just for the optimizer state.
So you're at 84 gigabytes of VRAM before you have even passed a single piece of data through the network.
Exactly.
It's like buying a compact car and then finding out the instruction manual requires 2 separate garages to store.
That is a brilliant analogy. Yes.
So what could possibly be so important that it requires double the memory of the model itself?
Well, the optimizer is trying to solve the physical terrain of the learning process. Those 8 bytes are actually 2 separate FP32 numbers, 4 bytes each.
Okay, what are they?
The first 4-byte number is called momentum, technically the first-order moment. And the second 4-byte number is called variance, which is the second-order moment.
Okay, wait. Listening to you explain this terrain, it reminds me of this analogy from the sources of a blind man trying to navigate.
Oh, the blind man on the mountain, yes.
Let's unpack that for everyone. Imagine standard gradient descent, the basic old-school way a neural network learns as a blind man trying to walk down a treacherous, dark mountain to find the lowest valley.
Because the lowest valley represents the lowest error in the model.
Exactly. He has no map, no vision. All he can do is feel the slope of the ground directly under his foot. If the dirt slopes down to the left, he takes a step to the left.
And on a perfectly smooth, bowl-shaped mountain, that works flawlessly. He just spirals down to the bottom.
But high-dimensional loss landscapes in neural networks are not smooth bowls, are they?
Not even close. They are nightmarish geographies. They have sheer cliffs, jagged ravines, and these massive, infinitely flat plateaus.
Right. So imagine our blind man walks into a steep, narrow canyon that gently slips downward along the bottom.
Okay.
He feels the steep slope on the left wall, so he takes a big step right, but he steps too far and hits the right wall. Now he feels a steep slope pushing left, so he steps left.
It just bounces.
Exactly. He ends up ping-ponging back and forth off the canyon walls, totally exhausting himself, barely making any forward progress down the actual canyon.
Yeah.
Or worse, he wanders onto a massive flat plain. The slope is basically zero. He feels almost nothing under his foot, so he starts taking these agonizingly microscopic steps. He'll die of old age before he crosses the plane.
And this is exactly why the first 4 bytes of the optimizer state, the momentum, exist.
Right.
Momentum equips our blind man with an inertia sensor. It doesn't just look at the slope under his foot right now. It keeps a running weighted average of all his previous steps.
So if he is ping-ponging left and right off the canyon walls, the leftward steps and the rightward steps cancel each other out in his moving average.
Exactly. The only consistent direction he has been moving is slightly forward, down the canyon.
That's genius. The momentum sensor ignores the walls and pushes him straight down the middle.
Yep. The noise is canceled out by history. And when he hits that massive flat plane, the inertia from all his previous downhill running carries him forward.
He practically sprints across the flat ground because his momentum tells him he was moving fast a moment ago.
Exactly. Momentum cures the bouncing in the ravines and the stalling on the plateaus. It is a massive upgrade to the learning speed.
That is incredibly elegant. But wait, that only explains the first 4 bytes. What about the next 4 bytes? The variance.
So, if momentum is an inertia sensor, variance acts as an intelligent shock absorber.
A shock absorber?
Yeah. Where momentum averages the gradients themselves, variance is a moving average of the squared gradients.
Why squared?
Taking the square of the gradient strips away the direction left or right, doesn't matter, and isolates pure magnitude. It measures how violently the slope is changing.
Okay, let's go back to the mountain. Why does the blind man need a shock absorber?
Because some parts of the mountain are gentle rolling hills, and some parts are terrifyingly steep cliffs.
Right.
If the blind man has a standard fixed step size, he might take a comfortable stride on a gentle hill and be perfectly fine. But if he takes that exact same standard stride while standing on the edge of a cliff...
He goes flying.
Exactly. The massive downward slope will launch him into the abyss. He will completely overshoot the valley and ruin the model.
So he needs to, tiptoe on the cliffs and run on the hills.
Precisely. Variance tracks this volatility for every single parameter individually. If a parameter is experiencing wild, massive gradients, meaning it is on a steep cliff, the variance value grows large.
And then what?
The optimizer looks at that large variance and mathematically applies the brakes, shrinking the step size for that specific parameter.
Oh.
Conversely, if a parameter has been experiencing tiny, stable gradients, meaning it is on a flat, safe surface, the variance is small, and the optimizer lengthens the step size to speed things up.
So it's a dynamic, self-tuning suspension system applied to 7 billion different wheels independently.
That is the absolute magic of Atom W.
Yeah.
Every single parameter gets its own bespoke learning rate, updated dynamically on every single step based on its personal history of volatility.
Okay, I want to tally up the physical real estate again.
To do it.
We have 4 bytes for the master weight. We have 4 bytes for the momentum inertia sensor. We have 4 bytes for the variance shock absorber. That is 12 bytes per parameter.
Yeah.
And we haven't even stored the actual gradient for the current step yet, which requires another 4 bytes. So we are at 16 bytes per parameter minimum. For our 7 billion parameter model, that is 112 gigabytes of VRAM. We have completely blown past our 32 gigabyte consumer GPU, and we are now requiring multiple massive server GPUs just to hold the math in a static state.
The physical space is the price you pay for the intelligence of the algorithm. You literally buy that intelligence with VRAM.
Now, you mentioned Atom W earlier. The sources specifically highlight Atom with a W, distinguishing it from the original Atom optimizer published years earlier.
Yes.
Why is the W so crucial that it became the gold standard for every large language model today? Why not just regular Atom?
The W stands for weight decay, and it represents a subtle but profound correction to the original math. Weight decay is a regularization technique.
What does that mean in plain English?
Its purpose is to prevent the neural network from just memorizing the training data. If weights get too large, the network becomes brittle. It overfits.
Like a student who just memorizes the test answers but doesn't actually understand the subject.
Exactly. Weight decay constantly applies a tiny penalty, pulling the weights back towards zero, forcing the network to distribute its learning across many parameters rather than relying on a few massive ones.
That makes sense. Keep the weights small, keep the network flexible. But didn't the original Atom have that?
It did, but it implemented it through something called L2 regularization,
Okay.
which mathematically mixed the weight penalty directly into the gradient before calculating the momentum and variance.
Oh, I see where this is going.
The penalty got tangled up in the shock absorbers and the inertia sensors. The history of the penalty was being tracked alongside the history of the actual learning signal.
Oh. So if a parameter was on a flat plane, its variance would be small, so Atom would boost its step size, right? But because the weight decay was tangled in there, Atom would also accidentally boost the penalty, pulling it to 0. It was literally fighting itself.
Exactly. The adaptive learning rate was distorting the weight decay. It was a mathematical mess. Adam W. solved this by completely decoupling them.
How so?
It calculates the momentum and variance using only the pure gradients. Then, completely separately, right before it updates the parameter, it just multiplies the current weight by a tiny decay factor, shrinking it slightly.
Just a little haircut.
Exactly. This decoupled approach keeps the adaptive learning rates pure while ensuring the weights stay healthy and generalized.
So we know what these 8 bytes are, and we know why we need them. Let's actually watch them work.
Sure.
I want to take the listener down into the mechanical engine room here. How does Atom W actually update a single parameter? What is the step-by-step assembly line?
It operates as a strict 4-stage pipeline. Imagine a parameter moving down a conveyor belt. It has just finished a forward and backward pass, so a brand new gradient has arrived. Stage 1 is updating the history. The system must calculate the new momentum and the new variance.
Walk me through the actual math of updating the momentum. How heavily does it rely on the past versus this brand new gradient that just showed up?
It uses an exponential moving average controlled by a hyperparameter called beta 1, which is almost universally set to 0.9.
Point net, okay.
The equation is take the old momentum, multiply it by 0.9, take the new gradient, multiply it by 0.1, add them together.
So 90% of the decision is driven by the historical inertia, and only 10% is driven by the slope the parameter is currently standing on.
Yes, it is heavily biased towards stability. And it does the exact same thing for the variance, but the variance uses a parameter called beta 2, which is usually set to 0.999.
Wait, 0.999, so the variance is 99.9% history and only 0.1% the new squared gradient.
Yep.
Why is the shock absorber so much more stubborn than the inertia sensor?
Because the magnitude of gradients can be incredibly noisy. A single freak spike in the gradient shouldn't immediately clamp down the brakes for the rest of training.
Well, that makes sense. You'd never get anywhere.
Exactly. The optimizer wants a very long-term, highly stable view of how volatile the terrain is before it messes with the suspension.
Okay, so stage 1 is done. The moving averages are updated. The parameter rolls down the belt to stage 2. The sources call this bias correction.
Right.
What bias are we correcting?
We are correcting the fact that at step 0, the history didn't exist.
Right.
When you start training a massive model, the old momentum and old variance are initialized as literal zeros.
Let me do the math on that.
Hmm.
If we are on step 1 and old momentum is 0, 0.9 times 0 is 0,
Yep.
plus 0.1 times the new gradient, the resulting momentum is just 10% of the actual gradient. It's artificially tiny.
Exactly. Because it's an exponential moving average, that initial 0 acts like a massive anchor, dragging the momentum down for hundreds of steps.
It's like a train trying to accelerate while still tied to the station.
That's it exactly. Bias correction is a mathematical formula that dynamically divides the momentum and variance by a factor less than 1 during the early stages of training.
To inflate it.
Yes, it artificially inflates the numbers to compensate for the 0 initialization. As training progresses to step 100, step 1000, this correction factor mathematically asymptotes to 1.
Effectively turning itself off once the train has built up natural speed.
Exactly. It's temporary training wheels.
That is brilliant. Okay, the anchor is removed. Stage 3 on the assembly line. Weight decay. We already touched on this. This is where Atom W earns its W.
Right. Before we actually use our corrected momentum and variance to move the weight, we just shrink the weight a tiny bit. We multiply the current weight by, say, 0.99.
It's just a gentle, persistent pressure, pulling the parameter back towards 0, maintaining the health of the network.
Precisely. And finally, stage 4, the final update. We bring the momentum, the variance, the learning rate, and the weight together.
What is the actual arithmetic that physically changes the parameter in the VRAM?
The new weight equals the decayed old weight minus a fraction. The numerator of this fraction is the learning rate multiplied by our bias-corrected momentum. This dictates the base speed and the direction we are moving.
Right, the inertia sensor drives the car.
But the denominator of the fraction is the square root of our bias-corrected variance.
Okay, pause. I want to make sure I completely understand the interaction here. If the variance is huge, meaning we are on a steep cliff, the denominator is huge.
Right.
And when you divide by a huge denominator, the overall fraction shrinks. The step size becomes tiny. The shock absorber hits the brakes.
Exactly. You nailed it. And if the variance is small, the denominator is small, so dividing by it actually amplifies the step size, accelerating the parameter across flat planes.
But wait a minute. If we are on a perfectly flat plane for a long time, the gradients are zero. The
Yes,
variance becomes zero. The denominator becomes zero. You can't divide by zero. That mathematically breaks the universe. The GPU would throw a NAN and crash the entire training run.
which is why there is one final hidden piece of the equation.
Let me guess, a cheat code.
Sort of, plus epsilon. Inside the denominator, PyTorch always adds a microscopic constant called epsilon, usually around 10 to the -8th.
Just to ensure the denominator is never literally
A
zero.
microscopic savior for the entire trillion-dollar AI industry.
That is so wild. Just a tiny piece of tape holding the whole thing together.
It prevents the math from exploding. And, when you step back and look at this entire four-stage process, you realize something profound.
What's that?
This incredible spatial intelligence, the ability of the model to dynamically tune the speed of 7 billion independent parameters based on their bespoke histories, is not free.
Right.
We are literally trading physical space in the HBM for training speed and stability. You cannot have the intelligence of Atom W without paying the physical rent for those 8 bytes.
Space equals intelligence. I love that framework. But as massive as this static memory requirement is, we calculated over 110 gigabytes for our 7 billion parameter model. The sources reveal that we are still ignoring the true monster.
Oh, we haven't even seen the monster yet.
Right, because the static weights and optimizer states are just the empty architecture of the brain. The real VRAM killer wakes up when the brain actually starts thinking. When we feed data into the model.
We are moving from the static structure to the dynamic flow, the activations.
Let's define that clearly. What exactly is an activation?
When you feed a sequence of text, a prompt into a neural network, the data doesn't just jump to the output. It passes sequentially through dozens of layers.
Okay.
Layer 1 performs massive matrix multiplications on the input data, creates an intermediate output, and passes that output to Layer 2. Layer 2 does its math, transforms the data again, and passes it to Layer 3.
So it's a bucket brigade.
Exactly. Those intermediate outputs, the electrical signals flowing between the layers, those are the activations.
But why do they kill the VRAM? Like, Layer 1 finishes its math and hands the result to Layer 2. Once Layer 2 has the data, Layer 1's intermediate work is completely useless, right? Why doesn't the GPU just delete Layer 1's activation to free up memory?
If you are only running the model performing inference to generate text, then it absolutely does delete them.
Oh, it does?
Yes. In inference, you calculate Layer 2, you instantly overwrite Layer 1's memory space. You calculate Layer 3, you overwrite Layer 2. This is why the memory footprint of inference is incredibly small.
Which is exactly why you, listening right now, can actually run a massive open source model on a consumer graphics card at home. Inference is aggressively memory efficient because it lives entirely in the present. It constantly forgets the past.
But training is fundamentally different. Training is ruled by the chain rule of calculus.
Calculus ruins everything.
It really does. To learn, the network must perform backpropagation. It calculates the error at the very final layer, and then it works backwards, layer by layer, adjusting the weights.
Okay, but how does calculus force us to keep the activations?
The mathematical formula for calculating the gradient of a weight in Layer 1 during the backward pass explicitly requires the exact activation value that Layer 1 produced during the forward pass. You cannot calculate how to fix the weight unless you know exactly what the weight produced a moment ago.
Yay. No, are you saying what I think you're saying?
During training, you cannot throw anything away.
Oh my God.
You must hold every single intermediate activation for every single layer for the entire forward pass, all in the VRAM at the exact same time. You have to store the entire history of the thought process until the backward pass slowly reaches them and consumes them.
That is horrifying from a hardware perspective. How big do these activations get?
Let's calculate the explosion. The rough formula for activation memory is number of layers multiplied by the hidden size, multiplied by the batch size, multiplied by the sequence length.
Let's unpack those variables. A modern large language model might have 80 layers. The hidden size, the width of the neural network layer, might be 800 and 192 parameters wide. Those are massive numbers, but they are fixed by the model architecture.
Right, the architecture doesn't change. The variables that cause the VRAM to truly explode are batch size and sequence length. Batch size is how many separate text prompts you are forcing the model to process simultaneously in parallel. Sequence length is how many tokens, how many words are in each prompt.
Let's say I'm doing a standard training run. Batch size of 32. I'm pushing 32 documents through at once, and a sequence length of 2048 tokens.
Let's just look at one single layer of math for that. 32 documents times 2038 tokens times a hidden size of 800,192 times 2 bytes for the FD16 format.
What does that equal?
That single layer produces roughly 1 gigabyte of activation data.
Okay, 1 gigabyte. Not great, but manageable.
And multiply that by 80 layers.
That's 80 gigabytes.
Now realize that inside each transformer layer, there is a subnetwork called a multi-layer perceptron, or MLP.
Oh no.
The MLP's job is to temporarily project the data into a much higher dimension to extract complex features before compressing it back down. A standard MLP expands the hidden size by a factor of 4, so the intermediate activation inside the MLP is 4 times larger.
Oh my God. So we aren't at 80 gigabytes. We are well over 200 gigabytes of memory just to hold the intermediate math for a standard batch of text.
Yeah.
And we still haven't touched the most infamous part of the transformer architecture, the attention matrix. Why is attention the ultimate boss-level VRAM killer?
Because the fundamental innovation of the transformer architecture is self-attention. It allows the model to understand context. But the mechanism of attention is brutally expensive.
How does it work?
Every single token in a sequence must mathematically compare itself to every other token in the sequence to determine relevance.
So if my sequence is the sentence "the cat sat on the mat," the word cat has to calculate an attention score with "the sat on the" and "mat."
Exactly. So if you have a sequence length of n, you must generate a matrix of size n multiplied by n. This is the attention matrix. And here's where you hit the wall of big O notation. The memory required for the attention matrix scales at O(n squared is quadratic.
So if I double my sequence length from 2,000 tokens to 4,000 tokens, the attention matrix doesn't double in size. It quadruples. 2 squared is 4.
Precisely. Now think about the massive long context models being released today, boasting context windows of 128,000 tokens, or even 1,000,000 tokens.
Oh, that's...
When you square 128,000, you are generating an attention matrix with tens of billions of intermediate floating point numbers per layer, per attention head.
That's astronomical.
The n by n matrix becomes so unimaginably massive that the activations suddenly eat up 90% or more of your entire server cluster's VRAM.
Yeah.
The 112 gigabytes of model weights and optimizer states we worried about earlier.
Yeah.
They become a tiny rounding error compared to this ocean of dynamic activations.
It sounds like a math problem that literally outpaces the physical manufacturing capabilities of the semiconductor industry. You can't just slap a terabyte of HBM onto a single GPU core. It won't fit. So how is the industry actually training these massive context models? We must be cheating somehow.
Oh, we are cheating brilliantly. The software engineering community has developed radical workarounds. The two most important are flash attention and gradient checkpointing.
Let's break down flash attention. How do you cheat a massive matrix multiplication?
You have to understand the physical layout of memory on a GPU. The massive pool of memory we've been talking about, the HBM, is located off the main processing chip.
Okay.
To do math, the GPU must pull data from the slow HBM, bring it into a tiny ultra-fast cache directly on the silicon called SRAM, do the multiplication, and then write the result back out to the slow HBM.
So the bottleneck isn't the math, it's the physical transit time of moving gigabytes of data back and forth across the chip.
Exactly. Standard attention calculates a piece of the n by n matrix, writes it out to the slow HBM, calculates the next piece, writes it out, and then reads the whole massive thing back in to apply the softmax function. It's incredibly inefficient.
So what does flash attention do?
Flash attention is a technique called operator fusion. Instead of writing the intermediate steps to the HBM, flash attention breaks the math down into tiny, clever tiles. It loads a tile into the ultra-fast RAM, computes the attention, computes the softmax on the fly, gets the final answer, and writes only the final answer back to the HBM.
Wait, so it literally never creates the massive n by n matrix in the main memory?
Never. The giant matrix only ever exists as a fleeting ghost inside the microscopic SRAM cache. Flash attention slashes the memory footprint by an order of magnitude and drastically speeds up the calculation simply by refusing to use the slow memory bus.
That is amazing. Operator fusion, fusing the steps together so you don't have to save the scratch pad work. Okay, what about gradient checkpointing? You said earlier that calculus demands we save every single activation for the backward pass. How do we cheat calculus?
Gradient checkpointing is the ultimate trade-off between time and space. If you don't have the VRAM to save 80 layers of activations, you compromise. You don't save every layer.
What do you do instead?
You save a checkpoint activation every, say, 4 layers. Layer 1, Layer 5, Layer 9.
Yeah.
You intentionally throw away the activations for layers 2, 3, and 4 to save memory.
But then how do you calculate the backward pass when you hit layer 4 and the activation is gone? The calculus breaks.
It doesn't break because you recreate it.
How?
When the backward pass arrives at layer 4 and finds empty memory, the GPU stops the backward pass. It looks for the nearest saved checkpoint, which is layer 1.
Okay.
It then physically reruns the forward pass math for layers 2, 3, and 4 right then and there, regenerating the missing activation on the fly. It uses the regenerated activation for the gradient and then instantly deletes it again.
Wow. So you are literally doing the forward pass math twice. You are dropping breadcrumbs every few miles, and when you need to remember the path between the crumbs, you just sprint back and walk the path a second time.
Yes. You trade about 30% more compute time because the GPU is redoing millions of calculations in exchange for a massive reduction in the VRAM footprint. You drop the memory scaling curve from linear to roughly a square root curve. For many engineers, trading time for space is the only way a model will physically fit on their hardware.
Okay, we've talked about the raw data. Billions of static FP32 weights, gigabytes of dynamic activation matrices. But how is all this data actually packaged? We aren't just pouring numbers directly into the silicon. There is a software container organizing this chaos. Which brings us to the vessel, the tensor.
If the numbers are the liquid, the tensor is the incredibly sophisticated glass holding it. At its most basic definition, a tensor is a multidimensional array.
Let's trace the geometry of that for the listener. Dimension 0 is a scalar. It's just a single point of data, a single number like the number 5.
Simple enough.
Dimension 1 is a vector, a line of numbers. Imagine a single row in a spreadsheet. Dimension 2 is a matrix, a flat grid of numbers, rows, and columns. That's the entire spreadsheet page. Dimension 3 is a cube of numbers. Think of a standard digital photograph. It has height, width, and 3 deep color channels for red, green, and blue.
Right.
And an n-dimensional tensor just scales that geometry up indefinitely.
Precisely. But the obvious question for any programmer listening is, why do we need a proprietary tensor object created by PyTorch? Python already has lists. Python lists can hold arrays of numbers easily. Why reinvent the wheel?
Yeah, Python lists are incredibly flexible. You can put a string, a float, and another list inside a single list. Why force everything into a strict PyTorch tensor?
Because the flexibility of a Python list is a complete nightmare for hardware acceleration. There are 3 critical reasons tensors exist.
Let's hear them.
First, parallelization. A Python list is processed by the central processing unit, the CPU, sequentially. It looks at the first item, then the second. A GPU has thousands of microscopic cores designed to do the exact same math operation on millions of numbers at the exact same time.
Right.
A tensor is structurally designed to be digested by those thousands of GPU cores in perfect parallel harmony.
Speed. The CPU is a single fast sports car making trips. The GPU is a fleet of 10,000 dump trucks. Tensors are designed for the dump trucks. What's the second reason?
Autograd, automatic differentiation. This is the true magic of deep learning frameworks.
Look so.
A Python list just holds data. A
Yeah.
tensor holds data, but it also secretly records its own mathematical history. When you multiply tensor A by tensor B to create tensor C builds an invisible graph in the background pointing back to A and B, remembering the exact calculus operation that created it.
It's a self-aware array of numbers.
Exactly. When you finally tell the model to learn, PyTorch just walks backward through that invisible graph, automatically generated the gradients for the backward pass. Python lists have no memory of how they were made.
And the third reason?
Memory continuity. This is the crux of the physical layout. When you create a Python list, Python asks the computer's RAM for space, and the operating system just scatters the data randomly wherever it finds an empty slot, connecting them with invisible pointers.
So the data is everywhere.
Right. Reading a Python list means the computer is jumping all over the physical RAM chip collecting the pieces.
Which is slow.
Violently slow. For a GPU to achieve its massive bandwidth, reading terabytes of data per second, it cannot jump around. It demands that the data be placed consecutively in a single, solid, unbroken physical block of HBM silicon. A tensor guarantees that the billions of numbers it holds are sitting side by side in the physical hardware.
But getting that solid block of data onto the GPU is notoriously difficult. The sources talk at length about the PCIe bottleneck. Let's explain the physical geography of a motherboard for a second.
Sure. You have your CPU and your system RAM on one part of the board. You have your massive, expensive GPU plugged into a slot on another part of the board. Connecting them is the Peripheral Component Interconnect Express Bus, the PCIe bus.
It's essentially a bundle of microscopic copper wires acting as a highway, and the sources say this highway is a massive traffic jam.
Oh, it is.
If I write normal PyTorch code, I initialize my massive billion-parameter tensor on the CPU's memory, then I tell PyTorch to move it to the GPU. Suddenly, I am shoving gigabytes of data through this narrow copper highway. It can take seconds or even minutes just to load the model.
Which is completely unacceptable for high-performance training. So PyTorch provides a bypass.
What's the bypass?
When you create a tensor, you can pass a flag. Device, CUDA. CUDA is the software language for NVIDIA GPUs. When you use this flag, PyTorch doesn't build the tensor on the CPU and move it. It sends a tiny instruction across the PCIe bus telling the GPU's memory controller to carve out the continuous block of HBM directly.
Oh, wow.
The data never travels the highway. It is born natively on the GPU.
And there is a specific PyTorch function mentioned that takes this speed run to the extreme, torch.empty.
Yes. Normally, when you ask a computer for a block of memory, say, with torch.zeros, the hardware finds the space and then dutifully scrubs it clean, writing a literal 0 into every single bit just to be safe. It takes time to scrub gigabytes of memory.
It's like renting an apartment. You want the landlord to clean out the previous tenant's trash before you move your furniture in.
Exactly. But torch.empty says don't bother cleaning.
It just takes the birdie apartment.
It instantly grabs a block of HBM and hands it to you, completely filled with the raw, dirty garbage data left over from whatever program used that silicon last. It could be fragments of an image, old network weights, random noise. PyTorch doesn't care. It is the absolute fastest possible way to allocate VRAM because it skips the scrubbing phase.
But isn't that dangerous? If I do math on garbage data, my neural network is going to output garbage.
It is extremely dangerous if you don't know what you are doing. You only use torch.empty when you know with absolute certainty that your very next line of code is going to completely overwrite that block of memory with your own calculated data. You are acting as your own memory manager.
Okay, so we've mapped out the physical reality. We have these massive, continuous blocks of HBM silicon holding billions of numbers.
Yes?
But here's the problem. Deep learning is just endless matrix multiplication. To multiply matrices together, the dimensions have to align perfectly. That means the neural network is constantly needing to manipulate these shapes.
Possibly.
It needs to flip them, rotate them, transpose rows into columns. But if moving gigabytes of data across memory buses is a massive bottleneck, how does PyTorch flip a billion-parameter matrix so fast? Does it have a hyper-optimized copying algorithm?
This is where we leave standard computer science and enter the realm of pure sleight of hand.
Okay, I'm ready.
The short answer is no. PyTorch does not copy the data. PyTorch lies to you.
I love this. PyTorch lies. Let's look at the actual code to prove it. Let's take the transpose function. Y equals x dot transpose. Let's create a tiny matrix for the listener to hold in their head. A 2x3 matrix. 2 rows, 3 columns.
Okay.
Row 1 is the numbers 10, 20, 30. Row 2 is 40, 50, 60. When I call transpose on this, I want to swap the rows and the columns. I want it to become a 3x2 matrix. The first column, 10 and 40, should become the first row.
And logically, on your screen, if you print the tensor, that is exactly what happens. It looks perfectly transposed. But the big reveal is hidden in the physical metadata.
Where?
Every tensor has a property called datapta to the data pointer. This is the literal hexadecimal physical address in the HBM silicon where the very first number is stored. If you check the data part of your original matrix X and then you check the data part of your transposed matrix Latakata, they're identical.
Wait, no, that can't be right. If I flip a matrix, the data physically has to move to be read in the new order, doesn't it? The 40 has to move up next to the 10.
Not a single byte moved. In the physical silicon of the HBM, there are no grids. Memory chips are one-dimensional. The data is stored in a flat, single-file line of numbers, 10, 20, 30, 40, 50, 60. When you call transpose, PyTorch didn't touch the data.
Then how does it act like it's transposed? If the physical numbers are sitting in the exact same flat line, how do I get a transposed matrix out of it when I do math?
Through the brilliance of strides. The physical memory is the raw material, but the stride is the instruction manual. It tells PyTorch how to jump through that flat, single-file line of physical memory to build the logical 2D shape you want.
Okay, let's break down the stride for our original 2x3 matrix.
For your original matrix, the stride metadata is a pair of numbers. 3, 1. Here is how you read the manual. The first number tells you how to move down a row logically.
Okay, so to go from the first row down to the second row, say from the number 10 down to the number 40, I jump exactly 3 spots forward in the physical memory.
Right. 10, jump past 20, jump past 30, land on 40. The second stride number tells you how to move right across a column. To go from 10 to 20, you jump exactly 1 spot. So stride 3, 1.
Got it. Jump 3 physical spots to go down a row. Jump 1 physical spot to go right a column. That recreates the 2x3 grid perfectly from the flat line. So what happens under the hood when I call transpose?
PyTorch simply swaps the metadata numbers. The stride becomes 1, 3.
That's it. It just swaps 2 integers in the instruction manual.
Yes. Let's trace the new manual. You want to read your transpose matrix. To go down a row, the first stride number is now 1. So from the number 10, you jump 1 spot and land on 20.
And look at that. Logically, 20 is now in the first column of the second row, exactly where it belongs in a transpose matrix.
Right. Now, to go right across a column, the second stride number is 3. From 10, you jump 3 spots past 20, past 30, and land on 40. Logically, 40 is now in the second column of the first row.
It's an illusion. PyTorch is just faking it. It didn't do any math on the numbers. It didn't move gigabytes of memory. It just handed you a new, reverse-engineered instruction manual that reads the old flat memory in a new pattern.
Exactly. Because modifying 2 tiny integer metadata variables takes 0 time and 0 extra memory, transposing a billion-parameter matrix is an O of 1 operation. It happens in constant time. It is instantaneous. This metadata trick is the only reason deep learning is fast enough to exist.
This is an incredible hack, but there has to be a catch. You can't just lie to the physical hardware forever. Eventually, the bill comes due.
The bill comes due violently, and it arrives in the form of a word that haunts every single PyTorch developer. Contiguous.
Contiguous memory.
By swapping the strides, PyTorch created a massive discrepancy. The logical shape you see on your screen is now fundamentally out of sync with the physical layout in the silicon.
Okay, let's look at your transposed matrix.
You want to read the first logical row, which consists of the numbers 10 and 40. But where are they physically? 10 is at the very beginning of the memory block. 40 is 3 slots down. To read one logical row, the hardware memory controller has to read 10, skip over 20 and 30, and read 40.
The physical memory is jumping around.
Exactly. The physical memory is no longer a sequential, uninterrupted block that matches your logical shape.
Yeah.
You are now what PyTorch calls non-contiguous.
And is that bad?
While the transpose function handles this perfectly, almost every other high-performance math operation in PyTorch, especially those written in highly optimized C++ or CUDA, is not so forgiving. They demand that the physical layout exactly matches the logical shape. If you feed a highly optimized matrix multiplication function a non-contiguous tensor, it either runs excruciatingly slowly or it completely crashes.
Which brings us to the grand finale of memory manipulation. Changing shapes. Often you don't just want to transpose, you want to completely reshape a tensor. Say, turning a 2x3 matrix into a flat 1x6 vector. PyTorch gives us 2 main tools for this: view and reshape. And the sources paint a very clear picture of their personalities. Let's call them the strict inspector and the pragmatist. What happens when you try to use .view to change the shape of our transposed non-contiguous tensor?
View is the strict inspector. It is designed to be as fast as transpose, meaning it wants to change the shape solely by manipulating the strides without moving any physical data.
Okay.
But when a view looks at your transposed tensor, it sees that the physical memory is jumping all over the place. It sees the non-contiguous mess, and it immediately throws a fatal red error. When an error.input is not contiguous, it refuses to execute.
It sounds like trying to saw a block of wood. Think about it. .view is like a hyper-fast, incredibly precise laser saw. It can instantly slice a block of wood into any dimension you want. But the laser saw makes one strict, unyielding demand. You must feed it a perfectly solid, continuous block of wood. That is contiguous memory.
It's a great physical analogy.
If you feed the laser saw a pile of scattered, glued-together scraps with gaps in between, which is exactly what our transposed, non-contiguous tensor looks like, to the physical memory controller the laser saw simply strikes. It refuses to turn on. It says, I cannot make clean mathematical slices through this chaotic physical mess. Fix it.
The math behind why it refuses is fascinating. The algorithm inside .view tries to calculate a new set of strides for your new shape. But the formula it uses relies absolutely on the assumption that the strides are monotonically decreasing, meaning the memory progresses perfectly sequentially.
And ours doesn't.
Right. When the memory is non-contiguous because we scrambled the strides with transpose, the mathematical formula breaks.
Yeah.
It literally cannot find a set of strides that will make the new shape work without moving the data. So instead of doing something dangerous, it throws an error to warn you.
Okay, so dot view is the high-performance diva. It demands perfection. Who is the pragmatist?
The pragmatist is .reshape, is the function you call when you just want the shape change and you don't care about the underlying physics.
Just get it done.
Exactly. When you call reshape, it does a quick background check. It asks, is this memory contiguous? If the answer is yes, .reshape acts exactly like .view. It calculates the new strides. It's instantaneous, zero memory overhead.
But what if I feed it my messy transposed tensor? What if the answer is no?
If the answer is no, .reshape sighs, rolls up its sleeves, and quietly does the brutal, expensive work in the background. It sends a command to the GPU to allocate a brand new empty block of VRAM. It then physically copies every single number over from the messy jumping arrangement into a perfectly sequential, contiguous order in the new block.
Oh.
Only after the physical copy is complete does it hand you your new shape.
So it literally builds a brand new solid block of wood for you to saw.
Exactly. But here is the massive danger for developers.
Yeep.
Reshape does this silently.
Oh, that's scary.
Very. You might write a loop that calls reshape thousands of times, thinking you are doing a fast, zero-memory metadata trick. But in reality, .reshape is secretly allocating gigabytes of new VRAM and performing massive slow data copies across the memory bus on every single loop. This is the #1 cause of sudden, mysterious out-of-memory errors that developers simply cannot track down. They think they are manipulating metadata, but they are accidentally duplicating massive physical arrays.
That is terrifying. It makes you realize how much PyTorch is hiding from you. What about the flatten function? We use flatten all the time to crush 2D images or matrices into a single 1D line before feeding it into a final classification layer. How does flatten handle a non-contiguous tensor?
Flatten is insidious because it defaults to physical reality, ignoring your logical illusions.
Yeah.
Let's go back to our transpose matrix. Logically, the first row is 10, 40, the second row is 20, 50, the third is 30, 60.
Right.
If you ask a human to flatten that logically, reading left to right, top to bottom, they would write 10, 40, 20, 50, 30, 60.
Yeah, that preserves the logical grouping we created when we transposed it.
But if you call flatten on the non-contiguous tensor, the PyTorch backend often ignores your modified strides entirely. It just looks at the raw data app tetra, looks at the physical memory block, and reads the silicon sequentially. 10, 20, 30, 40, 50, 60.
Wait, it outputs the original untransposed flatline? But that completely destroys the logical relationships I just built? It gives me mathematically incorrect data.
If you aren't rigorously managing your memory states, yes. The flattened tensor will contain the wrong spatial information, your model will learn garbage, and PyTorch won't throw an error because mechanically it successfully flattened the memory.
Okay, so how do we protect ourselves? If transpose creates this dangerous illusion and view crashes and reshape silently eats memory, how do we force the hardware to sync up with our logic safely?
By explicitly using the .contiguous function.
What does that actually do under the hood?
Calling .contiguous is an explicit command to PyTorch to stop playing metadata tricks. It forces PyTorch to allocate new memory and physically copy the data so that the physical layout in the silicon perfectly matches the logical shape defined by the strides. It transforms the illusion into physical reality.
So if I pull up the source code for a massive, state-of-the-art large language model, and I look inside the transformer multi-head attention blocks, I constantly see engineers chaining these commands together on a single line, x.transpose.contiguous.view. Now, the mechanics of that are perfectly clear.
Walk through what that chain is physically doing.
Okay, first, they call transpose. They're using the O of 1 metadata trick to instantly flip the logical shape of the attention heads without moving any data. But they know this makes the tensor non-contiguous.
Right.
So immediately they call .contiguous. They are explicitly choosing to pay the physical memory tax right then and there. They force the GPU to physically reorder the gigabytes of data sequentially so it matches the new transposed shape.
Right.
And then finally, they call .view. Because the memory is now a perfectly solid, contiguous block of wood, the strict.view function activates and instantly slices the data into the final shape needed for the matrix multiplication.
Exactly. Those engineers are not just writing abstract mathematical equations. They're acting as highly skilled memory architects. They are constantly consciously balancing the need for mathematical speed against the rigid physical limitations of the hardware's memory controllers. Every line of code is a negotiation with the silicon.
Let's sit back and look at the entire landscape we've mapped out today. We started at the absolute microscopic foundation, the single 4-byte FP32 parameter, a format agreed upon decades ago, meticulously engineered to balance scale and precision, keeping our models from freezing into zeros or exploding into nans.
We then uncovered how that 4-byte foundation is completely dwarfed by the heavy machinery of the Atom W optimizer, the invisible 8-byte tax of momentum inertia sensors and variance shock absorbers. We saw how the algorithm trades literal physical space on the microchip for the dynamic intelligence required to navigate treacherous learning landscapes without stalling or crashing.
We watched the VRAM footprint explode dynamically when we introduced the prompt, the terrifying calculus of the forward and backward pass forcing us to hold gigabytes of activations in memory simultaneously. We explored how the quadratic scaling of the attention matrix forces us to invent brilliant hardware cheats like flash attention fusing math into the SRAM cache to avoid the slow memory bus and gradient checkpointing, where we literally drop breadcrumbs and recalculate math just to survive the memory crunch.
And finally, we pulled back the curtain on the tensor itself. We exposed the brilliant lies PyTorch tells us with strides and data pointers, allowing us to manipulate billion-parameter matrices in constant time. And we learned the strict physical laws of contiguous memory that dictate when those illusions hold, and when we have to pay the iron price of allocating and copying real physical data.
So for you, listening right now, the next time you fire up a script and get that brutal out-of-memory error or a bizarre runtime error, input is not contiguous, you aren't just staring at abstract Python code anymore. You have X-ray vision. You can look through the monitor and see the physical constraints. You can see the 4-byte weights, the hidden 8-byte histories, the surging quadratic tides of activations, and the invisible metadata instruction manuals desperately trying to keep the physical memory from fragmenting. You aren't just a coder anymore, you are a manager of physical electricity in silicon.
Which leaves us with a final, vital question about the future of this entire field. We have built an absolute revolution, a trillion-dollar AI industry, on the back of the FP32 math standard and these massive memory-hungry optimizer states. We've completely accepted the premise that space equals intelligence. Atom W proves that if you give an algorithm more physical memory to track history, it learns faster and better.
But the hardware isn't infinite.
Exactly. As models grow from billions of parameters to trillions of parameters, the physical limits of silicon manufacturing and the speed of light across the PCIe bus become rigid, unyielding walls. We cannot just keep stacking bigger and bigger memory chips onto a motherboard forever. The heat and the latency make it physically impossible. So, how much more intelligence can we possibly squeeze out of these clever PyTorch hacks and SRAM operator fusions before we hit the absolute physical wall of our current hardware paradigms? Will we reach a point where we are forced to throw out Atom W, abandon backpropagation, and invent entirely new memory-free ways of machine learning that we haven't even conceptualized yet?
A physical wall requires a new kind of magic. That is something to mull over. Until next time.